All right, I will begin with a word of prayer once I get up here. Dearly Father, we thank you for this day again. I thank you for your students. Just ask you to bless our work today. Help us to glorify you, what we do, Lord. In my prayer, Lord Jesus. Amen. So relax. There's no surprise mission today. But it's probably because I ran out of time. Now, obviously, you should not be done with all of Mission 1 yet, right? Because we haven't gotten to all of those kinds of problems yet. But I would encourage you to at least to have tried the problems in Mission 1 that resemble the problems we went over in class last week, right? But the next kind of problem we should think about is what's called the Bernoulli. So a Bernoulli differential equation looks like this. dy dx plus p of x times y is equal to q, which is some function of x, times y to the power n. All right, this is a Bernoulli differential equation. And basically, it can be solved by a... trying to find it in here. I don't have it memorized. Z, or if you like V, I'll use Z for a change. Z equals to y to the 1 minus n substitution. All right. So let me, because it turns out that if you do that, it turns it into a linear differential equation, which you can solve. Let's see here. So I have an example for us. So here's my example. So we're up against y prime plus xy equals to xy cubed. Now I don't usually write y prime in class because it's harder to see. So let me change that to what that actually is, which is of course dy dx. All right. All right. So this has n equals to 3. So it's like a linear differential equation, but why is it not linear? It's not linear because you got a y cubed here, right? So that spoils it just being a plain old linear dE, which of course we could solve by the integrating factor method, and yay, we'd be done, right? Okay, so allegedly, if we make a z equals to y to the 1 minus 3, also known as y to the minus 2, also known as 1 over y squared substitution, supposedly magic things will happen for us. All right, so if that's the deal, then this means that like dz dy, right? dz dy. What's wrong with me? No. What do I want? So here's the deal. We're going to keep the x variable. We're just switching y out for z. All right? Making that substitution. So what I want to know is what's dz dx. And so that's d dx of 1 over y squared, because I trust the hint in my notes about that's how we solve this. All right, so that's a chain rule. So I've got minus 2 over y to the power 3 dy dx. All right. So let me just clean that up ever so slightly. What this says is that dy dx equals to what? dy dx is actually equal to like minus y cubed over 2 times dz dx, right? So I usually want to find a clean formula for dy dx when I'm working these problems so I can like substitute it in. See, because to make a substitution, I need to like replace the derivative with respect to the new variable, and then of course also I just need to make a change for the differential equation at large. But let's get to it here. So dy dx is actually minus y cubed over 2 times dz dx. All right, plus xy. But what's y equal to? Ooh, see, I don't like that. Yeah, let me leave it as xy for the moment. I'll show you why. I don't want to deal with square roots. There's a way around that. Xy equals to xy cubed. All right, so I haven't really made the substitution. I've only made the substitution at the derivative at the moment, right? I didn't do anything with these yet. See that? I just left them. So now what I'm going to do, I think will be helpful, is if we solve for dz dx, well, not for it, but like isolate it. So that's going to give me multiply by minus 2 over y cubed. So I've got like minus 2, oh my bad. So I've got 2x over y cubed, my bad. What is that? Y over y cubed is what? Y squared equal to, oh look at that, just I think minus 2x, right? So, oh man, yowzers. So going from here to here, multiply by minus 2 over y cubed, okay? And I did some simplifications while I was at it. Ah, but what is 1 over y squared?
Z.
That's z, right? So this is dz dx minus 2x times z equals to minus 2x. That is a linear differential equation at the linear ODE in z and x, right? So to solve that, we use the integrating factor method. What's my integrating factor here? Exponential integral of what? P of x, and the p of x here is? So we got a minus 2x for our p. All right, so that's e to the minus x squared. So now that we found our integrating factor, we multiply the differential equation by the integrating factor. That gives us e to the minus x squared times dz dx minus 2x e to the minus x squared times z is equal to minus 2x e to the minus x squared. All right. And remember what I said. I said if we did this process right, we're going to have like a natural check to our calculation. Can you see the reverse product rule here? What is this expression the derivative of?
E to the negative x squared z.
Yeah, e to the negative x squared z. That was inescapable. That had to happen if we did our integrating factor method correctly, and we did. And now we can integrate both sides, right? Integrate both sides. And this gives us z e to the minus x squared equals to, well, e to the minus x squared plus a constant, right? Because the integral of minus 2x e to the minus x squared is just e to the minus x squared, right? If you differentiate what I'm about to underline in green, you get back what we integrated, do you not? See that? This guy right here differentiates to give this by the chain rule. So that shows you that's the antiderivative. So I just integrate both sides. It gives me that. Now I can solve for z. Z is, well, apparently 1 plus c e to the x squared. But what was z? Remember? Z was 1 over y squared, yeah? So this is all equal to 1 over y squared, which finally gives us y is equal to plus or minus 1 over the square root of 1 plus c e to the x squared. And there you go. That's the general solution here to this Bernoulli differential equation. So if it's a Bernoulli differential equation, we make this particular substitution, and you can work it out in general, that if you make this substitution, it will convert it to a linear differential equation in the substitution variable, which then you can solve by the integrating factor method, and yay. So that's that. One more of these, and then I will cease and desist from the substitution problems, at least of this sort and variety. Listen, you could spend weeks and weeks and weeks on this. There are like endless substitutions to study, and in different parts of science and engineering, there are particular substitutions which are sort of native to that particular storyline in your subject matter. So I don't try to cover all those. I leave those. You'll discover those in the course where you use these things, if that happens. And if it doesn't, just, they're out there. Okay, so yeah, I told you. But this one here is this is a different kind of substitution. So this one is actually illustrating a concept that I don't tend to, it's less common that we need to do this, but it's kind of fun. So I wanted to show you. And I'll skip a lot of the details, all right, because our class time is precious. But the details are in the notes. And so if you have this differential equation in Pfaffian form, let's call it star, all right, then, well, this right here, it's not nice, all right, like, the various, it's not linear. It's far from exact. It's not a Bernoulli or anything so nice like that it has a name. It's just weird, right? But there is a certain beauty to it, right? It involves what? Square root of x squared plus y squared, right? And so that might make you think, well, maybe polar coordinates are a good idea here, right? And if you were to think that, you'd be right. If we put x equals to r cosine theta, and we put y equals to r sine theta, right? Then the differential of x is like cosine theta dr minus r sine theta d theta. And the differential of y is sine theta dr plus r cosine theta d theta. And if you put those two up into there, and you convert the x and the y coordinates over to r's and thetas as the appropriate trigonometry demands, and you simplify, what happens after a few lines is that differential equation is actually star, upon a change to polar coordinates, this thing actually becomes dr over r cubed is equal to the sine theta d theta. So in polar coordinates, that's what that differential equation looks like, you see? And so with a change to polar coordinates, we can solve that, right? So it's not bad to solve, right? We just integrate. The devil's in the details of this arrow, right? Okay? And there really is, well, let me finish this. So integral 1 over r cubed is what? Minus 1 over 2r squared, right? Add 1, divide by it, and that's equal to like minus cosine of theta plus a constant. Yeah. So, and, well, let me multiply this by r just for giggles. Minus 1 over 2r is equal to minus r cosine theta plus c. So if I convert back into, what's the word? Cartesian coordinates, it's minus 1 over 2 to the square root of minus 1 over twice the square root of x squared plus y squared is equal to minus x plus c times the square root of x squared plus y squared, right? So there you go. That's the implicit general solution to example 2. Yeah. I don't think I would have found that without this technique, right? Without changing to polar coordinates. Now this begs a question. Well, that's great that you did this, but when can I use polar coordinates? When is it helpful? And the answer is I have no idea. But I'm pretty sure that if there's not a square root of x squared plus y squared in the problem, it's probably a bad idea. And even if there is, there's no guarantee this comes back to something nice in polar coordinates. So my larger point is just this: making substitutions to change differential equations to something nicer is an art form, all right? And pretty much in this class, I don't hold you responsible for the art. I will basically I take your hand, I shove a paintbrush into it, and I say paint. And when I say that, I mean I suggest the substitution. I tell you, make a z equals to 1 over y squared substitution. I tell you, try to make an x equals r cosine theta, y equals to r sine theta substitution. Work that out, all right? And that takes it from being an art form to, well, just painting. So you can do that. But anyway. So let us continue on here. Unless there's a question. If there's a question, feel free. All right. One of the things we did early on was I wrote down the solution to cosine, like y prime prime plus y equal to 0, being a cosine, right? And we were successful in doing that. So that begs the question of, can we solve second order differential equations through techniques like we're using right now? Like, is it possible to solve second order differential equations using like a substitution, right? Can we do that? And the answer is yes, at a cost. And the cost is sometimes higher in one problem than another. Let me start with a rather benign problem. If we have a derivative, if there's no like term just with y, if everything has a derivative on it, then making essentially a velocity substitution works out real nice. So like an example I have of that. And this is actually going to be a natural transition for us into applications, which is what we're talking about by the end of today, because I'll talk a little bit about physics and such. But, oh man, where'd it go? That's not the one I want. Let's put it away. There we go. So suppose you're trying to solve y prime prime plus y prime, and I'm just going to make it equal to 0. It's x squared in the notes, but I'm going to keep it 0 here. So example 3. Here, let us say that the prime is t for the sake of making context with physics, right? So here y prime is dy dt, right? Y prime prime is d squared y. dt squared, also known as dv dt, right? If we let v equal to dy dt. So the velocity, right, this is velocity, yeah? What's the second derivative? Acceleration, yay. All right. See, physics isn't hard. You can say these words. Okay, so this is kind of a pain, but if we make a velocity substitution, substitute velocity equals to y prime, then star gives what? It gives dv dt plus v equals to 0. By golly, that one's pretty easy to solve, right? We could separate this thing and integrate it. Let's do that. So we got like dv over dv dt is minus v, which gives me dv over v equal to minus dt. Integrate both sides. We got ourselves natural log absolute value of the velocity is equal to minus t plus a constant. Exponentiate this thing. We get v is equal to like some constant. Let me call it v naught, because why not? E to the minus t. Yeah. So there you go. That's not a solution to the problem star though. That's a solution to the substituted problem. Yeah. How can I find y then? Okay, yeah. So you're like, put this equals. You're like, v was dy dt. So put that back there. Now integrate that. And you're right. We don't even need to separate. We can just integrate. Y is equal to like y naught plus, well, minus rather, v naught e to the minus t if we just integrate both sides. And I called y naught the constant because I'm wrong. what should I, let me make the constant c. If I wanted to write c in terms of the initial condition, if y of 0 is y naught, then what should c be? I was thinking c would just be y naught, but at a moment's reflection, I realized, no, that's not right. If I plug in times 0, what happens? I get y sub naught is c minus v sub naught e to the 0, right? Also known as 1. So apparently, c should be equal to y naught plus v naught here. So if I'm interested in my solution, the initial value problem, I've got y is equal to y naught plus v naught minus v naught e to the minus t. Which of course you could rewrite this as like y naught plus v naught times 1 minus e to the minus t. That might be like a nicer, there you go, that's a pretty nice form of the answer. Anyway, my larger point here is we solved the second order differential equation by making a substitution, didn't we? Yeah? Can we always do this? What's the problem? What made this substitution so nice is that we had a derivative on every term, right? What if there's not a derivative on every term? So I'll try to keep it relatively easy. Let's look at the simple example y prime prime plus y equals to 0, where y prime is dy dt again, okay? So here, you already see what's going to happen. I can't make just a y prime equals v substitution. That doesn't work. So what do I do? I use a dirty trick is what I do. A filthy, rotten trick. But it's a trick you maybe remember from physics. So here's how that goes. We let v, of course v is dy dt, right? But dv dt, we could also write as dv dy, dy dt. In other words, v dv dy, which gives me great joy to say for some reason. So I can recast the acceleration as v dv dy. And as such, making that substitution, I can trade out my y prime prime, which is this, right? For v dv dy plus y equals to 0. So, hooray, now we have what? Now we have a separable differential equation just in the velocity and y. We can solve this, I hope. So this gives us v dv is equal to minus y dy. Hey, this one's nice. Integrate that thing. We've got ourselves a 1/2 of v squared is equal to minus 1/2 y squared plus a constant, I suppose. And all right, so great. So this gives me v squared. Well, v is equal to like what? Square root of like 2c minus y squared, I guess. Plus or minus, yeah? Okay, but v was what? V was dy dt, right? So now we got dy dt is equal to plus or minus the square root of 2c minus y squared, yeah? Can we solve that? The answer is some of us can, maybe. It depends on how strong you are with trig substitution. Because this is a trig substitution. Or it's a basic integral depending on what you know. But if you see, this is dy over the square root. I'm going to put the plus or minus on the t, just to get it out of the way. 2c minus y squared plus or minus dt. So we integrate both sides. And that, I'll do the, the right-hand side's easy enough, plus or minus t, yay. This one, if we factor out 2c from that, what do we get? 1 over the square root of 2c, right? Dy over like the square root of 1 minus y squared over 2c. I should have made a... All right. Yowzers. Oh, fine. It is what it is. And there's a way to avoid some of this, but I have dug myself this hole, so we will continue digging. If I let u equals to, say, y over the square root of 2c, all right? In retrospect, it's apparent that 2c had to be positive, otherwise the solution's imaginary, which, well, that's another class, all right? So with that in mind, I make that substitution, and this becomes, you know, du is 1 over square root of 2c dy, but I've already got that there. So this is the integral of du over the square root of 1 minus the u squared, which, by the way, is inverse sine, plus a constant. So lo and behold, we have inverse sine, I'll get out of the way here in a second, of y divided by the square root of 2c is equal to like plus or minus t plus a constant. And if you take the sine of both sides of this, we get that y is equal to the sine of plus or minus t plus a constant divided by this other constant, square root of 2c. Or maybe multiplied, right? Multiplied, my bad. And a little bit of trigonometry later, you can see that this is really just c1 cos t plus c2 sine t for appropriate choices of constants c1 and c2. Although admittedly there's a little bit of trigonometry there between what I wrote and what I wrote, nevertheless it should be apparent that a sine of t is a solution to this. We've derived that rather than guessing it. I integrated and integrated again. I didn't guess it, I derived it. See the difference between guessing and deriving? Guessing is way easier. Guessing we did day one. I just said, hey, cosine's a solution to this differential equation because if you differentiate twice, you get back to minus cosine. You plug it in, it works. Yay. Yep. Question? No? Okay. Yep.
So is the goal to get it to a point where you can find an easy trigonometric function or something to integrate it more easily?
Well, just, I mean, as a point of order, I wanted to write the final answer like that. Because if you have a problem that you're trying to solve the differential equation, y prime prime plus y equal to 0, you don't want to cast your general solution as like sine of plus or minus t plus a constant plus square root of twice that. I mean, like, you don't want to write your answer like this. This is horrible. But this is just some trigonometry to go from here to here. Because we can do like adding angles formula for sine and cosine, and the plus and minus pulls out in that process and gets you to there. Yeah.
But the square root of 2c, what happens to that?
Oh, it gets absorbed into the constants. Yeah. I mean, the significance of the square root of 2c is it's the amplitude of the solution. And so this c1 and c2, the square root of c1 squared plus c2 squared, will be equal to the square root of 2c. That's the significance. Like that will bear out in the trigonometry if you go through it. But so this is what we can do if we don't have a derivative on every term. I guess the next question is, what if you had something like you know, could you solve that using my current technology? I think it's possible, but I'm not going to do it in class. If you want to try, you can. We will learn how to solve this easily, writing down an equation and just citing this. Like we just learned a method that allows us to just write down the solution in about 20 seconds for this problem in about 2 weeks. Okay. So like we don't keep doing things this way. I'm just showing you you can do things this way if you want to try to take the mystery out of why these are the solutions we find later, because we can in fact derive them. That said, I should probably go on to applied problems. Let's do that. So there are so many different applied problems to talk about. The first of which, of course, is physics, right? I mean, we've kind of already seen that here. What did we just do? What is the significance of example 3? You guys have had physics 231. You guys remember the spring mass problem? Right? You have a spring, you have a mass, you could have friction. I think what this would mean... Oh, actually, this is not the spring problem. My bad. So example 4 would be mass 1, spring constant 1. You could look at that like y prime prime equals to minus y. Or if you like, so like the last problem, if you think about the same mathematics, y prime prime, my bad, x prime prime equal to minus x. So in other words, you got like m x double dot equals to minus kx with m equals to 1, k equals to 1, right? You go through the math we just did, you see the solution is x of t is equal to like x naught sine of omega t plus some phase angle. You could write it this way. You're like, well, you're writing it a different way now. Fair enough, you got me. But here, omega is actually the square root of k over m as it happens. So we could go through a derivation kind of like we just did, and we'll come back to this one later. But my point is that this is like generally what happens. But for the example we just did, this one, thinking of y as x, all right? The spring constant's 1, the k is 1, so we just get, x is equal to sine t. That's the solution. This thing over here, on the other hand, would not be that. This would be something like mass times acceleration is equal to minus the, beta v. So usually this is like a friction force, right? This is a friction force. And so what we found in this problem is that the solution for, if you have a velocity-dependent friction force, which is what that is, right? The velocity-dependent friction force minus beta v, here beta equals to 1, right? The net force minus beta v in this context, mass was 1. What we found the solution was this. Does that make sense? What happens if you have a velocity-dependent friction force? As time goes to infinity, what happens? You stop, right? And that's what we see. As time goes to infinity, this thing goes to 0, and we're just left with y equals y naught. All right? Okay, so there's a couple physics examples we already did today. I just need to sell you on the fact that we were doing physics. You didn't realize it, but we were. So let's do something rather different. Let's look for what are called orthogonal trajectories. What's an orthogonal trajectory? So suppose you're given a curve or family of curves and find a new family which meets the given curve or family of curves at 90-degree angles. So if we want to capture this concept, did I not move the camera? Did you?
No.
Oh, okay. But I need to designate one of you guys as the camera dude. Wait a minute, I did move the camera.
Extra credit for that?
Extra credit. It's funny. So here's the thing. if we think about this in terms of slope, here's how it goes. dy dx of the given curve, right? Well, let me other way around. I usually say it the other way around. The dy dx for the orthogonal trajectory, the one we're looking for, how should it be related to the dy dx of what we're given? It should be minus 1 over dy dx for the given, right? Because then the slope will be negative reciprocal, which just says that wherever they meet, right, they meet like this. Oops. I'll try that again. All right, so maybe this is the given, and this is the orthogonal trajectory you're looking for, all right? So they're meeting at right angles like that. So you guys remember from like pre-calculus, this is the thing. If I want a line that's perpendicular to a slope 2 line, I do a slope minus 1/2, right? So same idea, but now with functions. So here's a good example of this. Suppose we're looking at x squared plus y squared equals to r squared, right? This is a particular curve, right? This is the circle of radius r centered through the origin. Let's find the orthogonal trajectories to this. All right, so here we go. 2x plus 2y dy dx equals to 0. This is the differential equation which corresponds to the given curve, right? How did I get that? I hope you guys know the deal. We just differentiate implicitly, right? So now, this gives me that dy dx for the given curve is like, minus x over y. So for the orthogonal trajectory, need to solve dy dx equal to what? Minus 1 over minus x over y. Also known as, cancel the minuses, we're just solving y over x. So separate, integrate, natural log the absolute value of y is equal to the natural log the absolute value of x plus a constant. Exponentiate that thing. Lo and behold, we get y is equal to k times x. Although admittedly we've missed an extraneous solution, right? Namely the vertical line. And so if you start graphing this, it becomes like, oh, well, I didn't need calculus to do this, right? I mean, come on, you guys if I'd given you a piece of paper and a ruler, you could have done this. What are the orthogonal trajectories to a circle? Right, they're just these guys. And if I did it right, everywhere where the circle intersects the line through the origin, it meets perpendicular, right? The perpendicular to the lines through the origin are the tangent lines to the circle. Now, in the homework I assigned last year, I actually had a problem which shows you how to set up not just orthogonal trajectories, but like trajectories that are with respect to an angle of the given curve. I forget the name, but it was one of the more insidious problems I assigned, like deriving that thing is pretty cool. So you might look at that. That's not something I expect you to memorize. I just think it's neat to derive. You can imagine yourself in the shoes of last semester's differential equations, where I actually made them work that out for homework.
You're really nice this semester.
I am nothing if not magnanimous. You should spread the word. Dr. Cook is easy. He's like so easy. You should take his classes. It's just like a walk-in. There's hardly anything to do in his class. It's so easy. Sorry. me move on here. So this is orthogonal trajectory, all right? Now, it can be sometimes, like it's annoying. Some problems are such that the constant which defines the family of curves, it doesn't go away when you do the implicit differentiation. And if that happens, I think you need to like solve for that constant to make it go. You want that constant to go away. Like if you can imagine yourself in the situation where, you know, imagine yourself in the situation when you differentiated this, the r didn't go away. Then you kind of don't want that. I don't know. It's more tricky that way. You got to be careful with those. So I'll just say that. I don't have an example offhand to show you, unfortunately. But I think there are some in the homework, so you'll see it there. But, so that's orthogonal trajectories in a nutshell. We could do another one. Example 6, like if you're up against x squared minus y squared equals to 1, you want to find the orthogonal trajectories to this. I got 2x minus 2y dy dx is equal to 0, which gives me dy dx is equal to like, you know, minus 2x over minus 2y, also known as x over y. So this is, okay, so for orthogonal trajectories, we need what? Dy dx equals to minus 1 over x over y, also known as minus y over x. So just to be clear, this is the given curve, and this is our desired orthogonal trajectory. It's important to keep those separate in your mind because you don't want to find yourself in the place of just solving the differential equation for the given curve. That would just get you back where you started, which would be, I mean, satisfying to show yourself you could do that, but not particularly helpful to solving the problem. But here we go. Guess what? We separate. Notice there's a minus now, but otherwise it's almost the same problem. Integrate. Natural log, the absolute value of y, is minus the natural log, the absolute value of x, plus a constant. So this gives us the absolute value of y is like, you know, plus or, exponential of the natural log of 1 over the absolute value of x, plus a constant, which gives me y is plus or minus e to the natural log of 1 over the absolute value of x, e to the constant, which of course we could rewrite as just like k over x. So y equals k over x. These are the orthogonal trajectories. And just to show you what's going on here, the given curve is a hyperbola. Does it open up or down or left or right? If I put x equals to 0, there's no solution, right? Which shows you that this hyperbola never crosses the y-axis. It turns around at x is plus or minus 1, and it looks something like this. I think. Yeah, y equals 0 gives me plus or minus 1 here. What does y equals k over x look like? What are those? Do you know what that is? Like what if I put k equals to 1? What is that? For example. That's this thing, right? There's k equals to 1. K equals to minus 1? This guy, right? In fact, here's the kind of cool thing. The given curve is a hyperbola. The orthogonal trajectories, also hyperbolas. I don't know if you knew this or not, but these red curves are hyperbolas. That the asymptotes of the hyperbola are the coordinate axes. Likewise, the blue curves are hyperbolas, again, with the x and y coordinate as axes. I'm saying axes, I mean asymptotes, right? The asymptotes of the original black, hyperbola there, that has asymptotes of y equals plus or minus x, right? Which I'll do in green here momentarily. So there you go. These are these y equals minus x, y equals x. These are the asymptotes of the original hyperbola. And I think those are actually also orthogonal trajectories to the original. I don't know about that. Well, these are definitely orthogonal trajectories to the. These are orthogonal trajectories to the orthogonal trajectories, but they never even intersect the original hyperbola, right? So I can't say they're orthogonal trajectories are to a given curve have to intersect the curve to ask about the question of perpendicularity of said intersection point. But the asymptotes never actually intersect the black hyperbola, right? So, but yeah, the interesting thing is like the black hyperbola, the orthogonal trajectories are again all hyperbola. It's kind of funny. In contrast, of course, the previous example, the circle, had orthogonal trajectories, which were lines. Right. So these are nice examples. Another thing to think about with differential equations is just like building a differential equation which satisfies a certain criteria you want, right? So what if I wanted to find a family of curves that was, say, increasing, excuse me, goodness gracious. Suppose I wanted to design, right, to engineer a differential equation which gave me solutions which were, say, increasing from y equals minus 1 to y equals to 3, and then decreasing elsewhere. What if I want to construct a differential equation which makes this happen? Can you do it? Of course, there's not a unique answer to this question, but I think the most sort of natural, simplistic answer comes from thinking, okay, how can I get a function which behaves like this? How about this? What I want is a parabola in y. If you think about y for a second, right? If this is y, I want it to be increasing from like minus 1 to 3, but I want it to be decreasing elsewhere. So like I think about a parabola in y. That's the kind of thing. It's got pluses here, right? And minuses over here. So an expression which does that is something like y plus 1 times y minus 3, you see? Now you probably never drew a graph where you put y that way, but if you think about it, you can. Yes, sir?
Now this is the derivative of that.
Yes. And so how about this? If I just put dy dx is equal to y plus 1 times y minus 3. Well, guess what? The solution set to this differential equation will have those analytic properties. And I actually solve a problem like this in the notes, similar to this. That's another thing. We could play these kinds of games, creating differential equations which will produce for us whole families of functions which have particular geometric traits that we wish to find. Right? We could do this. But the thing I really want to talk to you more about next class is if we're given a vector field. Right? You guys know what vector fields look like, right? The next question we're going to solve in terms of like, applied problem we want to solve is how can we find streamlines or flow lines to a vector field like this, right? How can we find a curve which lines up with the vector field? Like, how do you do that? Can we solve a differential equation to do that? And it turns out in the plane the answer is yes, we can. And I will show you how to do that next time. So anyway. And of course, we probably should work like a mixing tank problem and other more physics, et cetera, et cetera.